Hello, welcome to another video of CS360, and in this video we'll cover this concept of dovetailing. Okay, so dovetailing is basically a technique where we can use one Turing machine to sort of simulate infinitely many other Turing machines. What do we mean by that? So let's just give an example. Suppose you have the language, this language, language A of all Turing machines M, such that there exists a string W for which this Turing machine M accepts. Okay, so A consists of all strings that are descriptions of Turing machines M, such that there exists a string that you could give as input to M to cause M to accept. Okay, so not included in A are the Turing machines that reject all strings. Okay, so we want to show that A is recognizable. Okay, so how would we do this? So let's try to construct a Turing machine. So let's try to construct a Turing machine to recognize A. So let's call this Turing machine T for a second. So, you know, we're given as input some string. We can assume it's a description of some Turing machine. If it's not a description of a Turing machine, we can just reject. We can check this formatting and reject. Okay, but suppose we are given a description of a Turing machine. Then what can we do? Then we can try to simulate run M, basically have T simulate this machine M it was given on the empty string. Okay. The problem with a step like this is that this machine might never halt. So what if M of epsilon never halts? Okay, and remember that we can't know whether a given machine is going to halt on a given string. So T has no way to know whether this machine will halt or not, not in general, because that's asking it to solve the halting problem. So it can try to simulate M of M on the empty string, and if ever it does halt, then of course we're good. We know that this machine halted. But if it never halts, then T will never know to stop. It doesn't know if it just maybe didn't wait long enough. So this is a bit of a bad thing to do. We don't just want to run a machine that might not halt forever, okay? Because the thing is, if we did do this step, right? So if we did simulate M of epsilon, if this was part of the code of T, and if the next line of code said to simulate, simulate M on the string 0, okay, and then we can try to simulate. So, simulate M on the string 1. So if this was the code of T, then this second line might never happen because T might get stuck forever on the first line. So this is the problem, that it looks like we're telling T to do these steps, but actually not. These steps don't necessarily happen because some of the early steps might run forever, and then you never get to the later steps. Okay, so even if M were to accept 0, okay, so if M accepts 0, then of course we know that the input was an A, so T should accept. But even if that's true, that M accepts 0, T will never get there because M might loop on epsilon. So T might never get to seeing that M accepts 0 if this is the code of T. So what we're going to do instead is something called dovetailing, which is basically asking T to try to run all these machines in parallel. Now, the problem with trying to run all the machines in parallel is that we really want T to run M on infinitely many strings, right? We want to run M on the empty string and M on the string 0 and then on the string 1, M on the string 0, 0, M on 0, 1. Here I'm assuming the alphabet is just 0 and 1, so we're assuming here that sigma is 0 and 1 for simplicity. So this is, of course, all the strings. I'm writing them here in lexicographic order. So this is ordered by length and then alphabetically after the length. So I can order all the strings in this lexicographic order and run M on all of them. But even if I were to try to do it in parallel, then the thing is there's infinitely many such machines to run. So even if I told T runs one step of each of them, so I could try run one step. Oops, one step of each of these. The thing is, it will never finish running one step of on all the strings, because on all of these runs of the machine, because there's infinitely many. So you'll never get to the second step. So if you first want to run one step on all the machines and then run the second step on all the machines, you'll never get to this part where you're running the second step on all the machines, because you're trying to simulate M on infinitely many strings. So this strategy to try to kind of run them all in parallel at once doesn't quite work. Okay, so what we'll do is we'll basically draw a little chart. So we'll basically draw a chart where basically in this column, so the rows are basically going to be labeled by which machine to run, which run of a machine. So this is going to be M of epsilon and M of 1 and M of 0 and then M of 1 and then M of 0, 0, M of 0, 1. So these are all the rows of my table here. Okay, so and my columns is how many steps. Let's just call it number of steps. Okay, so here we're going to do the first step, the second step, the third step, fourth step, fifth step of this run. Okay, so we'll just draw this table. Okay, and what we want T to do is we're running, T is trying to basically fill the whole table. We're basically trying to run every machine for every number of steps. Okay, so we sort of want a strategy to walk through this table such that we will eventually cover any given cell of the table. Okay, so right, I mean, there's infinitely many cells of the table. Okay, but what we want is that for any given cell, like let's say this cell over here, with a star, for any given cell, we want T to eventually reach it. Okay, so we want T to eventually simulate M on 0, 0 for 5 steps. Okay, after some finitely many steps of T. So after some finitely many steps of T, we want T to have simulated M of 0, 0 for 5 steps. Okay, why? Because maybe M of 0, 0 accepts after 5 steps, and then T will know to accept the string the string M, because it found some string that M accepts. It found the string 0, 0 that M accepts. So there might be a cell here that has a star, which means that cell is an accept for the machine M on that string, and T, if such a star exists, T should eventually reach it after some finitely many steps of T. Okay, so we want some strategy of walking through this table such that for any given cell, eventually, after finitely many steps, we will reach that cell. Okay, even though the table is infinitely big. Okay, and note that the first thing we were trying to do of running M on epsilon, then M on 0, and then M on 1, the first strategy we tried basically said that T should walk along this grid like this, like basically in that direction. But if we just try to walk in that direction, so if our strategy was go in this first arrow direction until you reach the end, and then once you reach the end, start the second arrow, then the thing is you'll never reach the end of the first arrow. This m of epsilon might not halt. You might be stuck running it for more and more steps to infinity. So you will never reach the second arrow. So this strategy does not work. Okay, so another strategy here, sorry, just undo these arrows. So another strategy that we were saying is try to run the first step on each machine. That's actually the strategy of, of doing a down arrow like this, where you run the first step of m on epsilon, the first step on m on 0, first step on m on 1. And then after you're done all of the first steps, you run all the second steps and so on. But of course, that doesn't work either, because you'll never finish running the first steps of all the machines, because there's infinitely many machines that you're running, infinitely many runs here. I'm on infinitely many different strings. So that doesn't work either. Okay, but what you can do is you can do any strategy that does eventually cover any one cell. So you can do, for example, a strategy where you walk something like this, for example. And this is where the name dovetailing comes from, because like you're kind of covering parts of the graph that looks like this triangle over here is supposed to look like a dove's tail. So this is kind of where the name dovetailing comes from. But maybe a simpler way to walk through this graph is to say, okay, first we will run the first machine for one step. So we will cover this one first. So this is our step one. So step one is we cover the cell. And then we will run the first two machines for 2 steps each. So then we will do like basically this kind of strategy. So we walked like this. Okay, and then we will do the first 3 machines for 3 steps each. So at the first step, so basically we're doing something like this: 5, 6, 7, 8, 9. So basically after that step, we've covered this square. Okay, and then we run the first 4 machines, the 4 runs for 4 steps each. So then we cover this bigger square, this 4x4 square, in terms of what we've looked at, what we've run. And then we run the first 5 machines for 5 steps each. Okay, and then we cover this 5x5 cell. And note that any given cell will eventually be reached. Okay, so T, using this strategy of running the first machine for 1 step, then the first 2 machines for 2 steps each, the first 3 machines for 3 steps each, the first 4 machines for 4 steps each, eventually for any given run here, for any given run that you're looking for, and for any given number of steps that you want to run it for, eventually T will run that machine for at least that many steps. Okay, so if M accepts any string here, if M accepts any W, no matter how far down, as long as it's some finite number of steps down, and no matter how long it takes M to accept W. Okay, so that's sort of saying no matter kind of how far this way, this cell is where M accepts. Eventually, T will simulate M on W for that many steps. Okay, so if this is like K, sorry, if this is in the kth column, okay, and the Wth row here. Okay, so eventually T will run M on W, will simulate M on W for at least K steps. Okay, because eventually it will run the first N machines for N steps each, where N is some number bigger than K and bigger than the lexicographic numbering of W, basically. So, and then at that point, T will notice that M accepts W. And at that point, T can just stop this whole nonsense and just accept, because that means that T saw M accept some input string W. And therefore, this input M accepts some string, and T can safely accept. Okay, so the code of T would be something like for, for k. So this is like a pseudocode. So it's like an infinite for loop on k. And then, run first k machines. For k steps each. And here by first k machines, I mean, I just mean to run, in our case, we're running m on different strings. So run m on w for first k strings in lexicographic ordering for k steps each. Okay, so and then accept if any accept, if any run accepts. And that's it. So this basically is the pseudocode for T. Remember, T is only recognizing this language. So T might loop forever if the input M, so this is like T on input M, right? So T here, it's only trying to recognize this language A. It's allowed to run forever if M never accepts any string. But note that if M does accept some string, then T will not run forever. T will in fact accept. Okay, because eventually you will reach that string and you will run M on that string for enough steps, and you will see that M accepts, and then T will accept because you will reach this second step, and T will accept. So so this machine T will accept if M accepts any string. Okay, and so this is the dovetailing trick. It sort of allows you to run T in parallel on infinitely many machines. So like you're sort of running infinitely many machines in parallel in the code of T. Okay, and this is what is used to show that the recursively enumerable languages, like the languages that can be printed out by a Turing machine that's connected to a printer, are the same as the recognizable languages. Okay, and that's kind of because if you have a recognizing machine, then you can simulate it on the first string for one step, and then on the first two strings for 2 steps each, and the first 3 strings for 3 steps each, and so on. And then whenever it accepts some string, you can print it out. So you can have a printer that implements this dovetailing simulation of the recognizer on all possible strings, and then it will print out all the strings in that the recognizer ever accepts. So therefore, if your language is recognizable, then it's enumerable. There's a printer that prints all the strings in the language, but nothing else. Okay, and conversely, so if you have an enumerator, if you have a Turing machine that prints the language and nothing else, then to recognize where the string is in the language, you can just start running the printer and see if it ever prints your input string. If it ever prints the string that's given to you as input, then you accept. If it never prints the string, then you'll just keep running it forever. So this is a way to recognize a language given an enumerator for that language. Okay, so in one direction we use this dovetailing trick in the direction of converting a recognizer into an enumerator. We use dovetailing there. All right, so this is a useful trick when dealing with Turing machines. It comes up a bunch.